Okay, so we're going to start our introduction to logistic regression. So, welcome to week 6. So, we're going to do a thing called logistic regression. So, what does this do? So, imagine we've got a motivating example. So, what we've got here is the classic logistic regression example, where they took beetles and they exposed them to different concentrations of carbon disulfide. And then they measured how many beetles died because they wanted to use it as an insecticide. So what we've got here is we've got a concentration, how many beetles were exposed, and how many died. So what we've got here, to some extent, if you can think about it, is we're counting the number of success and failures, where success would be the death of a beetle, and failure would be that it lives. And obviously we have grouping. And the problem is, what we'd really like to do is be able to say, what's the probability of death on a certain concentration? Because we'd like to kill most of the beetles, but we don't want to use too much insecticide because it's a nasty, toxic chemical. So the question is, what concentration should we choose? So what we do is we want to get a relationship between concentration and, in this case, the probability of death. So how are we going to model this? Well, that's fine. You can say, well, what we've got in the previous one is we have a fixed number of trials. Each beetle is independent. We've got success or failure. So you should recognize this as a binomial model. If you don't, quickly go back to probability stats and just recap it, or get onto Wiki and check it. And what we'd like to do is we'd like to have a model that says yi, which is the number of deaths, has a binomial distribution where ni is the number of beetles we exposed and pi is the probability an individual beetle dies. And then what we'd like to do is we'd like to relate this pi to the xi, where xi is the concentration. So we want a model where pi equals fxi. So we can see that relationship. And we can say things like, if I increase the concentration by 1 unit, how does that affect the probability of death? Well, the simple thing you can do is go, fine, I'll just do linear regression. I'll have my pi as my response variable. What we could do is we could take the observed probability for each group, and I could say that's beta 0 plus beta 1 xi, where xi is my concentration that group was exposed to. But the problem is there's nothing in here that makes sure that pi I lies between 0 and 1. And pi I is meant to be a probability, so it should lie between 0 and 1. And there's no constraints here. You know, this concentration should get large enough that this becomes huge, greater than 1. Or we could have such that we could end up with certain slopes and intercepts that this could be negative. So we need to constrain it somehow. So we're going to basically add in a constraint. And that's what we do. We call it a link function. So first of all, let's take that structure we like, the beta 0 plus beta 1 xi, the linear regression part. I'm now going to call this e to I. And then what I'm going to do is I'm going to equate e to I to this thing here. Instead of having e to I equals pi, which we had in the previous one, what we've got here is we've got the log of pi over 1 minus pi I. And this thing we call the logit. So in the end, what we do is we can equate these two things, and we're saying the logit of pi I equals beta 0 plus beta 1 xi. Okay, so why did we do that? Well, the first thing is, the nice thing about the logit is, if pi I lies between 0 and 1, when I take this, eta can lie between minus infinity and infinity. So we've got a function that will map minus infinity to infinity, which is what our linear transform could be. Oh, sorry, not linear transform, our sort of beta 0 plus beta 1 xi could equal. But that's going to lock pi I between 0 and 1. The other nice thing is it's invertible. I can actually get pi I, if you rearrange this, is the x of e to I over 1 plus the x. This is the exponential of e to I. So the logit and its inverse are strictly increasing, so it's nice and easy. You're not going to have multiple solutions. The other thing is, you've seen this before. Think about it. This is a probability over 1 minus the probability. This is the odds of pi I. And we're taking the log, so this is called the log odds. And when we get to odds ratio, we'll discuss this further. So here's the curve. The nice thing is eta could go all the way to minus infinity to infinity, but the good thing is our pi is locked between 0 and 1. So that's good. We've got a function now that our beta 0 plus beta 1 xi could be any real number, but the pi I is locked between 0 and 1, which is what we want. So let's see about Beetle's data set. I will do a case study where we actually fit the logistic regression. I'll show you how to do that in the case study. But once we get that, we get the results is this. The the log of pi over 1 minus pi I. So notice it's not just a yi, it's the log of a odds, is equal to minus 60.pi6 plus 34.15 times concentration. So I can plug in my concentration, I can get my log odds. Or I can rearrange that and say if I wanted the actual probability, I can put in my concentration, put it into this equation, take the exponential 1 plus the exponential, and that will give me the probability. And here I've got it. What I've got is I've got the concentrations on the x-axis. Each one of these is one of those experiments where we had a load of beetles. So what I calculated here is the proportion of the beetles that died. So as you can see, as concentration increases, that slowly moves up. And the red line is the fitted logistic regression curve. Now, the interpretation is pretty much the same. Basically, what does the slope mean? Well, the slope means if you increase x by 1 unit, then the beta 1 tells you the increase in your y. But remember now, y is our logit of pi I. So it's not the increase in probability, it's the increase in the log odds. So then we'd have to undo that to get how much you increase the probability. And the rate of probability change is not constant. And you can see that in the previous picture. You can see the probability sometimes increases slowly, then it increases quickly, then it increases slowly again. But the main thing is that is telling us about the increase in the log odds. So for example, in our beetle example, we had a slope of 34.15. So if I increase the poison concentration by 1 unit, I get an increase of 34.15 in the log odds. The other thing I want to point out is before, this was our linear regression. We had our response variable, we had our intercept, our slope, plus we added our noise term. The interesting thing in logistic regression is we don't have what we call an additive noise term. There's not an extra noise term that's gone. Because if you think about it, this is our model plus this. And so you can say, well, where's the random variation? The random variation comes in this bit here because it's binomial. That's where the sort of the noise part. We've modeled the probability, but you know with a binomial, if the probability was say 0.5, sometimes you can get half of them, sometimes less than half, sometimes. So that's where the random variation. It's not an additive error term. It's built into the actual definition of the distribution we're using. Okay? So there's your introduction to logistic regression. Next week, we're going to say, well, how did I get those coefficients? So we'll look at maximum likelihood estimation. And also, we're going to start looking at inference. You know, is that slope significant? Can I do ANOVA? Things that we've done in linear regression. So the next video this week, I'm actually going to pop over to R and show you how to do this beetle one in R. Okay, see you next time.